Hello everyone, welcome to ECS CDM 12 Media Computation, the last lecture edition. We just talked about how we will be sending out assignments for the presentation slots for next week. Make sure that you see this as soon as we post it, so you will know when you're presenting. And as you know, there is a grade bump bonus for presenting on Tuesday as opposed to Thursday. So we want to compensate you a bit for the extra time, for the increased deadline for those of you presenting on the earlier date. Today we're going to be talking about 3D and sound, two topics that we've been touching on, that you've seen examples on, but I want to put a finer point on their usage. I want to show you some code, I want to show you some examples, so you can see how the palette you've already built with processing can be extended into these domains. All right. So as a notion, if you want to follow along, if you want to play the examples, some of them require, particularly the sound examples, require that you install a sound library. You can do this through, in processing, through, as I load it here, it's in help. I'm sorry, it is in Sketch, import library, and then there's a few default ones here. Sound is typically one of them. If not, you can go into the manage libraries ... which indicates that there is another dialog box to fill, where you get a list of all of the libraries, including a filter box where you can type in sound or 3D, and you'll see all the libraries related to those. For today, we are sticking with the Processing Foundations libraries of sound and 3D. The author will be Processing Foundation and not a random individual, I believe. Let me correct. Yeah, the Processing Foundation is the author of these. And that will just take a moment for processing to install those libraries for you, download them, unpack them, put them in an appropriate system directory, so your code, all of your processing libraries can then, your processing sketches can then use those capabilities involved in those code libraries. Oh, right. How many of you are aware of the novel Flatland? One person? Two people? All right, so this is a novel about a world that exists only in 2D. There is no third dimension. Here's a little clip that kind of shows this off, where actually one-dimensional beings are talking to two-dimensional beings.
Or describe this to me.
Then go away!
Hasn't it occurred to you that you could...
Okay, for some reason sound is not working. It's because I muted.
Move in some other direction?
I muted too hard. Okay. Tech Audio, Crestron.
Towards which your side is facing.
What?
Never.
What do you mean by side?
There is before and behind.
Nothing more.
Fine. Let me show you. Here, I'm going to move into your world. Here I come. There. Can you see me now?
Yes?
But
You're only a point!
Well, to you I'm only a point, but in fact I moved into Lineland. Now, I'm going to continue to move, and from your perspective, I'm going to vanish. What did your majesty say now?
Charlatan!
tricks!
Come back!
How did you do that?
I moved out of Lineland. Convinced?
If you had any sense, the smallest particle of...
You ask me to believe that there's another world? You say there's another motion besides forward and backward.
But when I ask you to show it, all you can do is babble and practice magic tricks.
You must be a madman, or dimensionally deficient.
You 6-inch idiot! You think you're the perfection of existence, but in reality, you're the most imperfect. You say you know the world, but all you see is a point. You can't even see lines. Well, I can. In fact, I am a line of lines, a square. In my world, as superior as I am to you, in my world, I'm nothing compared to the greatest of polygons.
I'll pierce you through.
Die, evil creature! Die!
All right, so that is a feature-length movie based on this book about different beings of different dimensions having conversations with each other. And so this like can undergird the difference between one dimension and two dimensions. And since we've been working mostly in two dimensions, we are three-dimensional beings. We know things have depth as well as height and width. Right, so that is the transformation we'll have to go through, handling that extra complexity from going from rectangles to cubes, from going to ellipses to spheres. That is the implications of moving from 3D to 2D. We also talk about this in Schiffman chapter 14. All right, the mysterious third dimension. There was Simpsons shorts about this, where the two-dimensional Homer Simpson becomes three-dimensional and discovers depth. Probably discovers more Duff beer along the way. So moving from 2D to 3D, we add a third dimension. We've been dealing with positions in X and Y points. So how do we represent where you are? So X and Y points, X vertical, Y vertical, X horizontal, but depth. That's our Z value. So by default, we're using Java 2D. But there are 3D modes. You can set them. So you can use P3D, OpenGL. OpenGL is the commonly used standard open graphics library for three-dimensional rendering. And it's hardware accelerated. So you may need to import the OpenGL library if you use Processing's 3D library import. It should take care of all of this for you. So the commands then are now naturally extended. Instead of translate moving in an X and Y, it actually has a Z component now too. So you can translate up, down, left, right, forward, backward. Rotation becomes more complicated now, because in 2D, rotation is only in 1 degree of freedom, right? You rotate the image around like you would move a paper. Well, now with rotation in 3D, you have to pick the plane that you rotate, where the paper is. In this case, you can rotate around it the x-axis, the y-axis, or the z-axis. We'll show some examples. Rotate was in radians before. The default here, for rotating in 2D, there's an implicit z-axis that we rotate around, right? You pick a center and you rotate around the center. Well, that center perspective is sort of like you looking down onto the paper, you looking down onto the screen, and then rotating around that central point. That's an implicit z-axis that we were dealing with 2D rotation. With 3D, we have to make it explicit. So, for instance, in 2D, if we wanted to rotate a rectangle by 45 degrees, we would translate that rectangle to the middle, assuming rect mode to center, and then we would rotate by 45 degree radians and then translate it back, and that would get our 45 degree rotation. So where you translate to, where you set the center, the origin, that's your pivot point. You can put it anywhere you'd like. Conventionally, if you want to rotate an object, you put that pivot point on the center. The implicit z-axis is now looking down onto that 0, 0 origin. Now with rotation in 3D, you get to pick the command. You get to pick which axis you want to rotate around. And you still rotate around it by radians. Object example, my headphones. You want to rotate around the Z? Z is forward and backward, you rotate around that. You want to rotate around Y? It's like this. You would rotate around X? It's like this. Roll, pitch, and yaw, for those of you who are pilots. And for those of you who have played games, you're familiar with this, right? Given a game controller, how do you handle 3D motion? What's an example? Certainly some of you have played a game in 3 dimensions. Huh? Yeah, so how, what moves you in which directions on the joystick? Yeah. So on the left thumb, what does it do? Like when you press the left thumbstick on, let's say, Yeah. So you press it up, you move forward, right? You press it down, you move backwards. So that's the z-axis control. What about left and right? What do those do when you move that thumbstick to the left and right? Yeah. So x and y directly would be strafing, right? So what happens? So in some games that's set up. In some games it's a bit of a rotation, right? And then you typically have camera control on the right stick, right? Which implicitly changes where forward is, right? So it's actually a multi-axis rotation. And it gets even more complicated when your camera is a third-party camera instead of a first-person camera. It's a third-person camera, an over-the-shoulder cam, or maybe even if you're playing a MOBA or something, right? The camera is actually looking straight down. And so that changes what movement is like, where directionality is, where forward is. Right? So handling this complexity is interesting. And the rotation order matters. Right? So let's see, if I rotate around the x-axis, then I rotate around the y-axis, we get this. But here, if I rotate around the y-axis, and then I rotate around the x-axis, we're actually in the opposite position, right? So the actual order matters here. Unlike when you did like some scaling and translating and rotating, you could do those in any order. They're operations that commute. But rotation does not. So here's some differences between two rotation orders. So at the top, we have our box in Y, this two-dimensional plane denoted by the brick color, right? And if we rotate 90 degrees around the Y, that flips the brick's directionality by 90 degrees. And then if we rotate around the Z, that flips that whole thing down, so you can see how it has this ordering now. But if we do Y, then the Z, then the X, it's in a completely different position. Does this make sense? And typically you can talk about things in white-handed rule for rotations, right? If you lift out your hand, you make a fist, and then you want to rotate like clockwise around. Like if you have a positive rotation, you'll actually go towards the direction your fingers are curling. And so there's a left-handed versus right-handed axis rotation methodology because you can do either in 3 dimensions. They're just the inverted properties of one another. So often if you see like 3D modelers, particularly those who are just starting to learn the craft, you'll see them like do weird hand rotations. And it's them like using what they know in this simple, this handed rule to understand when they do an operation, when they change the rotation and scale things, like where will it go? Because it can get complicated when you're dealing with like bones upon bones, seeing where they rotate, and then you want to like handle the thumb, but that handling of the thumb depends on all of the positionality and rotation and position and translations of all of the bone structure before it, leading to like the central point in the spine where the model is based. So this gets interesting. Oh, right. I have a laser. It's right now pointing forward. I want to point it at 10, 10, 10. What rotations would I do to pull that off? What's a good one to start with? Yeah.
Sorry, but where'd you hit it again? When you pointed the laser at him.
Yeah, so so in our coordinate grid, we are the origin. Our laser is pointing directly down X.
Yeah.
Right? So you may do this with your hand as well. This may help you. We want to go, it's 10, 10, 10. So it's that point that we want to point at is 10 to my right, 10 up, and 10 in. 10 in front. So I have this here. And we kind of want to, like rotate where I'm looking to get to 10, 10, 10, right?
It sounds like it's gonna be like X, Y, then Z, N, or...
Okay, well, X is this axis, so if I rotate around X, it'll do this,
Okay. Y.
right? If I rotate around Y, it'll do this.
Uh-huh.
If I rotate around Z, I'll do this.
Okay.
What do you think? And this will be impenetrable for people watching the recording later. I'm sorry. You can come to office hours and we'll stick our hands out and do this. What do you think? Needs to be up there. All right, does Z matter? Would I rotate around like this? Would this matter? No, not really. So we're looking at a combination of X rotation and Y rotation. Or around the rotation around the X axis and the Y axis. So rotating around the Y axis would move like this, right? So that seems to be a component, right? That would be useful. Rotating around the X axis moves us like this, right? Is that useful? Yes. All right, so how do we combine the two? Yeah.
So it's just Y, X, and Z. Yes.
Yeah, we don't think we need a Z in particular.
Oh, no, okay, no.
Because I guess if we moved like Y up, then we rotate around Z, it would, curve it around in a circle,
Mm-hmm. Okay.
which could work. You could use Z to solve this. It's a little more complicated. I mean, ideally, you'd probably just do,
Y, X.
a Y or an X rotation around X, and then rotation around Y, right? And that laser pointer would shoot out as a ray.
Okay.
Yeah, so an X rotation and a Y rotation. Does that make sense? All right. Hopefully you have engaged your mental facilities plus your physical facilities enough to understand some rotation. I didn't see a lot of engagement with a lot of folks, so this could be on the final. You should maybe engage with it. All right, transformations, scale. So now scale is interesting too. It's not just shrinking and expanding around a central point. Here we actually can scale each axis individually. And we could before with X and Y, right? If you had a rectangle, you could only scale it in the X, which would expand its length and not its height, or you could only expand it in the Y, which would expand its height but not its length, not its width. So, particularly with scale, we did both at the same time, which would make it bigger and smaller uniformly and not change its aspect ratio. You could do the same thing in 3 dimensions. So if you just set a scale value that's a float, it would scale each dimension by that amount with the depth and height. Now you have the facilities here to scale each independently. So if you had a cube, you could make the cube taller by stretching Y, wider by stretching X, and deeper by scaling Z. And we're back to push matrix and pop matrix, everyone's favorite. This is the reason why we primed this in 2 dimensions, push and pop. Originally, it was kind of just useful for setting pivot points for us and doing some relational animation, so like a car plus a wheel. That was handy for push and pop matrix. But in 3 dimensions, push and pop really matters a lot. Because you have more hierarchical relationships between structures. Where am I in 3 dimensions according to the door? Where is my elbow in 3 dimensions according to my shoulder, which is in a relationship, a matrix relationship, a scale translation relationship with my my spine, where everything connects, or really my clavicle, like all this motion here. Like if I have my arm out, I rotate 90 degrees around the Y, and then I rotate, so if I did elbow rotation, And then my shoulder rotation can be an arbitrary other configuration, but this still holds, right? And so there's this hierarchical relationship between different matrices that hold scale, rotation, and translation that matter, particularly for characters and things that are animated. This is why we have the bone rank systems that you may have seen in models, where you can change the location of an elbow by dragging its bone around. Well, that's modeled after sort of like how human bodies work, and modeled after push matrix and pop matrix, where each individual joint, each individual articulatable bit has its own matrix, which holds its rotation. But these work the same as they did in 2D and 3D, in 2D as they did in 3D, or work the same in 3D as they did in 2D. Simple explosion. We'll look at some examples after we go through this. In 3 dimensions, you have something that's akin to the real world, right? The real world, as we understand it, as we experience it as humans, is in 3 dimensions. Who knows, a 4th dimensional entity may come and laugh at us, and we may try to attack it, just like the 1-dimensional entities did to the 2-dimensional entity in Flatland. But simulating something in the real world in a 3D digital or virtual environment, that takes some work. And we typically just make the math to find the basic approximation. One cool example of this is the flocking algorithm, which was made by Craig Reynolds near the Bay Area. This is a pretty famous example of computational animation. And he modeled a bunch of flocking birds they basically looked at the starlings in the bay, looked at their dynamics, and made a computational model of those. So if you look up Boids, B-O-I-D-S, you can find the classic examples of early animation algorithms. So modeling these things is an interesting intellectual task, and sometimes is research. But what we want to do is what is the algorithm? What is the simulated model to model a thing exploding? How do you translate and rotate and scale all the little bits and particles that come out of an explosion to make it resemble or even accurately reproduce one in the real world? Here's one that we'll look at an example of. This is an example of exploding one big thing into many little pieces. All right, so there's a bunch of push matrices for each little item that you want to move. Pardon the formatting, got a little wonky when I put it into presentation mode. So for each X and Y, we want to specify the object offset. So the small object within the block, it should grow and move over time. Right, so let's say you had a rectangle and you want to explode that thing in 3 dimensions. Well, you need to find low explodable bits. In this case, an example, we'll use a bunch of sub-rectangles that comprise the big rectangle. And when we explode it, we want each one of those to fly out, rotate, and spin in a way that looks like an explosion. Right, and this is where this simple algorithm comes in. Let's actually, maybe this is a good time. Okay, so we'll look at that. Just keep this in mind. So this is an example of a small, inadequate for most uses simulation, but it's one that fits in a slide. It's one that you could grok and understand if you put some time into it. Our 3D drawing primitives are box and sphere instead of rect and ellipse. When stroke and no stroke now draws the wireframe. Are you all familiar with wireframes in 3 dimensions? Okay, we'll take a look at this. So basically, instead of having a box, you'll have all the edges that connect the box by points, and only seeing those edges and taking away the box texture is how you do wireframes. And you can color the outside of these 3-dimensional objects, the inferred surface of the boxes and the spheres with fill. But that's a basic version. For a lot of 3D applications, you want to use a texture to fill in that surface. And I believe Armpreet talked a bit about this on the video lecture. So he went over 3 dimensions, basics of OpenGL, like fan drawing, square drawing. He even went over some UV mapping. So that's where this comes in. Putting a color onto an object based off an image, a texture image, is UV mapping. So 3D computer graphics, you can see Building World is like building a movie set. So you have a bunch of models, right? If this was a virtual world, we'd have a 3D model for the chair, for the backpack, for the coat, for the headphones, for the virtual character in front of you. But you would also have lights. You would have a camera. So where are you seeing the world through? If you put on a VR headset, you're seeing it. There's a mapping of the camera to the VR headset, and you can manipulate the camera by moving your head around, by walking forward and walking backwards. It uses the basic notion of an accelerometer, so something can see how acceleration and therefore position is changing in 3 dimensions through a tiny little spring that moves back and forth. So if you ever used your phone to look at the night sky or something and do the constellation map over it, or use the Measure app on your phones to see how big something is, that's actually using the accelerometer, which infers 3D motion, right? So that is attached. You have an accelerometer on a VR headset, and as you move around, it's mapping your real-world motion to a rotation on a camera, which is a viewport into a 3-dimensional world. As you move your head, the camera is translated and rotated. And what's interesting is even with VR, we are taking these three-dimensional representations, and we're still putting them on a screen. The screen are flat screens, usually 2 displays, usually OLEDs these days, that are just in front of each eye. And we're relying on the human brain's ability to see through each eye and then take 2 incoming streams of photons, and our brain infers a 3-dimensional image with depth from those incoming photons. And so we're relying on that capability of the human brain to see depth, to look at a 2D image and see depth in that, even though it's a flat plane. This is how 3D works on TVs, right? TVs are flat, displays are flat, but we can still infer depth within the image. 3D graphics does the same thing. It actually models things in depth and distances, and then flattens that out through perspective division into a 2-dimensional image, which then we consume. All right, lights help create the surface. So they show how surfaces are lit. Like in here right now, I'm sure you see some shadows on my face because this light's at an interesting angle. Well, things like ray tracing and photon mapping are how we do lighting for 3D worlds. Ambient light, directional light, point light, spotlights, specular color. All of these are aspects of lighting in 3 dimensions. All right, so we made 2D planar objects with 3D transformations, and we can create 3D objects. So here's how you would create your own 3D object. To make a simple polygon, you would say, hey, I want the next vertices that I give you will be a shape. That's what begin shape means. So every vertex call until end shape is called are considered part of the same 3D object. Right, okay, so we're making an object that has 3 vertices at 50, 50, 150, 50, and 150, 150, right? So it's making a triangle. So once you call close, it connects all of those shapes together with edges. Each sequential point gets pulled together with an image in this basic version. But there are other ways to do it, and I won't belabor this since you had a good example with visuals previously. You can draw points, lines, triangles, triangle fans, triangle strips, quads, and quad strips. Those are your basic ways of interpreting a set of vertices and using those as a shape. All right. So most of the time, doing this is a waste of time. We have better tools to make shapes, like Maya, Studio Max, Blender, 3ds Max. So we can make models in software that is good for making three-dimensional models, and then we just simply import those into processing. The classic file format that we use is our OBJ files, object files. All right, let's look at some examples. So the examples, as always, are in the examples folder in the class materials Google Drive folder. And we'll be looking at the 3D folder, some images in here. So first, let's look at simple objects. Code editor, processing is loading. All right. So we have the X dimension of a light. We're setting up a basic window. We're using OpenGL as our as a parameter to size, basically denoting that this is a three-dimensional window instead of the two-dimensional window default. It's not Java 2D. Now it's OpenGL. So we draw a background. We say no stroke, so we don't want to display the wireframe. We make a directional light. So the light is positioned at 200, 200, 200. And it's where it's looking at, like where the light is shining from that position. Since the directional light, the direction is, it's pointing at X light, 0, -1. So X light will control, like if we're a light up here, X light will control like which point it is looking at. So we're controlling the X dimension of the point it's looking at, and then we are saying that its X is the second parameter is 0, so that means it's pointing straight ahead. It's not up or down, so it's pointing straight ahead. We can vary it left and right, and then it's pointed at -1, which is convention. Like usually straight ahead is negative in the Z space. No, I'm sorry. Since it's pointed ahead of us, it's pointing at -1. So we're having a light that does this, pointed back at the camera. There we are. And so we're putting the sphere in the middle of the screen. We're setting its fill color, and we're drawing it with a radius of 150. All right, and notice that we are changing X light as we drag the mouse around. So we're changing where the light's pointing on the X-axis. Okay, that's been a description. Let's actually see something. All right. Ooh, okay. Let's change this here. Okay. All right, so here's our sphere. That light is now pointing straight at it. So notice that light is more pronounced here, but it falls off at the edges, just as you would expect a light on a ball to do. Now I'm going to click the mouse and drag it around. We're changing where the light is pointed, where we're moving that light around on the X-axis. Now you can see as you move the light around, it changes where the sphere is illuminated. So it's not a circle, it's a sphere, because when the light moves around it, it's not flat. All right, any questions about this? First 3D object look. Once again, we're not drawing the wireframe. Directional light, translate. So we draw in the middle. We set the fill color to green, and we draw a sphere. Yes?
So you're able to manipulate the light through just the mouse press right there?
Yeah, so we're changing the X light variable, and the light is positioned at 200, 200, 200, but where it's pointing at, we're changing the X location of where the light's pointing at.
Gotcha.
All right, let's look at another example. This will be the icosahedron. All right, so now we have subclasses. We have points and int threes. So this one, we're making 3 golden rectangles. We're using the golden ratio to make a structure out of a bunch of small triangles. So this is I don't expect you to understand all this right now, but you can see that we're making new points. Each position that we want to configure in 3D space needs point values. So we're making planar values here. And so now we're going through each one of these values and we're making new points. And we're setting by default, we're giving them default values. And then we're doing a little bit of math to scale things appropriately. So we're not just making a plane, we're scaling things for depth and motion to position them properly. And then once we get all those, we're adding in our x, y, and z values of all of our x, y coordinates. We're making something that basically has like 7 rectangles. And we're not setting the fill, so we'll just get the edges. Right. And so now as we've done that, we've made the basic shape here in setup. Now we want to move it, fill it around, translate it, do some things with it, and draw. Which is why we have begin shape, going through all the vertices, close shape. And we're doing this here instead of earlier because we want to be able to manipulate it. We want to be able to play with it. I don't have time to go over all this code. I encourage you to look at this on your own, but let's see what's going on. Right? So now we're drawing this 3-dimensional structure. And we can spin it around, right? So what I did here is we're drawing the X, Y, and Z planes so you can see when we rotate where is the original axis. So 0, 0, 0 is right in the middle where these 3 planes intersect. And then we have the axes on all the intersections of the planes. And the math that we're doing, the triangle drawing we're doing, is connecting all these individual triangle bits together. Does this make sense? At a high level? Lovely. So let's look at a lighting example real quick. Get a better idea of how lights work. So here we're enabling a directional light. I guess this is the same as the examples before. Never mind. I had it renamed twice. Let's look at rotation. So now you can see an example of us rotating a box around the origin. You can see the wireframe on the circle here. When I click, we add in the lighting model. When I hit W, we can add and remove the wireframe. So the wireframe is exposing the actual vertices of the object. So all these edge points is a vertex. Each one of the corners in the box is a vertex. Spheres are more complicated, so it's hard to make something that looks round and smooth with basically triangles, which are flat. So the more triangles you put in here, the smoother it looks, the more circle-like it looks. All right. So we have surface control, ambient, emissive, shininess, specular. All of these control how something looks. So you can see the carpet, right? When a light shines to the carpet, you don't see like a shiny bit coming up from it, right? There's no concentrated bit of light or reflection. But if you look at something like this metal box here, you look at it and if you move your head around, you'll see that you can see a concentrated portion where the light is reflecting strongly. You can do this on any sort of like surface that has a high specular value. Like this floor, I can see the reflection of light. I can see a portion of light that is stronger than things around it based off reflections. On the carpet, I don't see that at all, right? So they have different specular values. Emissive things emit light, like the projector, like my screen. Most things don't actually emit light. The chair does not emit light, but it does reflect it. Shininess also controls reflectivity. It's related to specular. Now, how we deal with this in modern media is we use shaders to help determine these material properties. Shaders are little programs that run first on each vertex when an image is being processed. And then they run on each pixel when the final screen is rendered. There's where you can do things like bump mapping, where you can use shaders to control the outline of like a shield on a character. Shaders are very powerful. And if you want to do more interesting three-dimensional or even two-dimensional, in some cases, art, shaders are very interesting. I encourage you to go to ShaderToy, the ShaderToy website, and you can see what people have done with just these simple shaders. It's pretty fantastic. So with shaders and with texturing, with UV mapping, you can wrap an image around a bit of 3D geometry. Like you can map a flat map onto a sphere and create an approximation of a spherical Earth. We talked about the camera enough, where you can position, aim, and tilt the camera. With 3 dimensions, we have the power to turn off perspective, so things aren't perceptibly smaller the further away they get from the camera. Right? So because most of our graphics libraries are 3-dimensional, when you play like a 2-dimensional game or look at a website, these are all they all have 3D capabilities. But when you turn off perspective vision and you're only in orthographic mode, which means things don't get smaller as they get smaller closer as they go further away from you or closer to you, then you can start like laying tiles and sprites on top of each other. So the background sprites aren't scaled down perspective smaller than the sprites that they overlay, the sprites that are overlaid on top of them. Right? Websites, color boxes, the drop-down hamburger, all of these are layered in front and on top of each other, but they aren't subject to perspective shrinking and scaling, shrinking and increasing in size. It's very handy. Orthographic perspective is great for folks who want to do 2D things. Perspective is for 3D. All right. I want to look at just some more examples here for 3 dimensions. Let's go back to code editor here. Okay, we've got line example, simple drawing, simple objects. I want to look at the explosion. All right, here's our simple explosion. So here's the code that we looked at earlier. Right, so for each little particle that we have in our explosion, each bit of the exploded thing moves and rotates and is translated around. So this is where that actual math happens of where each individual things go. Let's take a look at how the explosion looks. All right, so here is our rectangle. Let's blow it up. Right, so this is the explosion. When you click it, you can run it. You can stop it at any point because we're controlling the simulation. Right, so we're controlling each one of these exploded particles. We have to simulate where they go, how they rotate, how they move. We have to give all that information to the computer through our algorithmic description, i.e. this, to pull off this explosion effect. Now when you are in a 3D movie making utility, when you're using something like a CG tool, Blender, Maya, etc., those tools are there to help you define these algorithms, define how the particles move. Usually there's particle system utilities, you can change their properties. Well, all of these properties that you change inside these editors simply help you parameterize something like this. They change all the little individual values so that each particle has its own particular characteristics, its own particular movement patterns. But when they actually render it and run it, when you see the explosion happening, there's code like this under the hood. Controlling the movement. So it's all very algorithmic. Let's see, is that the last thing I wanted to show for 3D? I think it is. I think we're good. All right. Let me prep the sound stuff. There we go. All right, any questions about 3D before we move on to sound? Oh, yes, go ahead.
In terms of the camera movement, is that like an extra thing that we have to add into the processing software? Like would we have to take it from external sources or does processing inherently have the camera?
Yeah, processing as a camera. We didn't see it in the examples here, but you can change the camera coordinates in the camera. You can change its translation and its rotation.
Okay.
We used the default camera, which was simply at 0, 0, looking down, straight down the z-axis.
Okay.
With no rotation in any direction. It's not scaled, or it's not translated anywhere. Just straight ahead. But you can call camera. You can give it its 6 parameters, aka its translation and its rotation values. So it's very easily doable. Like if you you could simply emulate like mouse-controlled first-person shooters by simply scaling X and Y with mouse X and Y, or rotate with rotate the radians of the X and Y, or I guess yes, around Y and around X with the mouse X and Y. So that would make you pan around the screen like you were a head swiveling around. You could easily pull that off, even for your project, perhaps. All right, sound. So starting in processing 3+, there's a sound library. I'm glad we're processing 4, and this just happened in the middle of the quarter that they upgraded the sound library to be stable and usable. So now is a great time to use processing sound. I'm sorry, was that a hand or... Okay, it is hairplay. There we go. So the sound library, easy to install and use. Sketch, import library, add library, select the sound, click install, wait a bit, you're good to go. Now the thing you have to add at the top of the file is, now there's this code library hanging around that does sound for you, but you need to tell your sketch that you want to use it. So at the very top of your sketch file, you want to put this. You want to import. So import means bringing in some external libraries, some external functionality, some externally defined classes into your project. So you import processing.sound.star. So processing, so this is a hierarchical thing. There's a big processing, what we call a namespace, basically just a way to organize all of your libraries. The processing has a bunch of libraries in it. One of them is sound. And we want to take in everything, star, from that sound library and use it. So, sound using the movie class, I kind of kept this in for legacy. I don't recommend you use it. We'll look at a better example. I just wanted this in here in case it was necessary for someone. But we're going to be looking at the basic sound library, but there are also other libraries out there, the Open Sound Control Protocol. So this interfaces with MaximSP and Pure Data for those of you who have done some algorithmic composition. I'm curious, has anyone here used MaximSP or Pure Data? Ooh, no digital musicians in the room. Okay. These are really cool visual programming applications for making sound. They're really interesting. All right, and third-party libraries are available for processing, such as Sonia and Minim. These are how you install them and play with them. We're not going to focus a lot on these. I just wanted this here in case you wanted to enhance your projects with sound. With some code examples on how to use sound with Sonia. Sonia is very, very much like the sound library and processing, which we'll look at momentarily. So sound files, audio in, you can have noise, various background noise applications, brown noise, pink noise, white noise, blue noise. There's all these various types of noise out there that you can use. You can use oscillators to change the sound waves. You can use filter effects, low pass, high pass, reverb. Are any of you familiar with these sort of like notations of sound? Any of you? Yeah, you've handled some of these. You've maybe done some synth work. Yeah, okay. This is also very interesting stuff. So we gave you that lecture going from like cathode ray tubes to 3D animation that Arampreet gave you. There's also a lecture that I have around about sound files, like how do you go from pressure waves in the air to the cochlear organ in your ears that vibrates little hairs at various frequencies, how that gets translated into sound. Okay, so how do you take those sound envelopes and our ability to recognize it to make different pitches, different noises, different tones, different timbres? All of this is all related. If you're interested in information, I'm happy to give you a recording of a lecture from another class that describes this. All right, so here's the processing library example. Whoops. Oh, I accidentally made that gray when it should be black. My bad. So you import processing.sound. You want to define a sound file, a ring. Once again, this is a reference. It doesn't have an instance associated with it, so ring isn't filled in. In our setup, we make a window 400 by 400, and we want to give something to ring. So we use new and the sound file command. So the sound file is this. This just means the application we're working with is the current one. This you can just like take for given for now. But what we want to load is dingdong.wave. So it takes a wave file, turns it, reads it, puts it in the sound file data structure, and that new instance that holds the ding-dong wave is then pointed at by ring. And a mouse click, we simply do ring.play. Let's take a look. This is basic sound demo. Same code. I'm just clicking. I really got to get inside. I'm being chased. Oh no. Oh. Yeah. So we played sound. It's really easy to integrate sound into your sketches. And, you know, we looked at this before when I had the microphone out and had it hooked up. You can use input as an example. So here we're using, just like that previous example, where we have an amplitude processing, bit of functionality that's part of the sound system. We have an audio in object. Our audio in object simply looks at audio in. It looks at your zeroth recorded or your default input device, your default microphone. So like this has a microphone. My headphones are attached to Bluetooth, have a microphone. This Blue Yeti is a microphone. My default microphone right now is set to the Blue Yeti. So when I run this, that 0, the default audio value, will be mapped to my system sound setting default input device, which is this. And then we want to start it up. We want to start sampling from it, start getting the bits from that it's delivering to the computer, use it as an input. And then once we started it, we can do the amplitude analysis library. We give it that input source as well. So now what we're drawing is the output of the analyzer. So we're getting a number afloat about what the current amplitude of the sound is, and then we're printing it. We're also changing an ellipse based off. We're scaling the ellipse based off that analyzed amplitude value. That is sound input sketch in the sound folder in the examples. So here we are, like same thing. Input. Hello. Right? Oh, did I not switch it over? Oh no. Okay, okay. Sorry about that. Sometimes I get a little caught up in the management of all the windows. It's a lot going on the screen. Whoop, that was explosion. One moment, one moment. Sound input. Here we go. Hello. Right, so very reminiscent to what we've done before. It is seeing the amplitude or like instantaneous volume of sound, and we're scaling this purple circle, magenta circle based on that amplitude scale. Right? What did I do? Okay. Sound. Input example. I guess that was, that is what I wanted to show. Now I wanted to recontextualize that earlier sound demo that we had used. Okay, going back to it. Oh, what did I call it? I've used weird names. Leaf with sprites. Well, no, it wasn't Water Strider. Stare at. Wasn't Sprout. It's a weird wiggle box. Where did I put this thing? These are old sound examples. Did I move my... Oh, that's right. I didn't give it to you because I couldn't give the copyrighted file. I have it in another folder. I just confused myself. Pardon me. Workbench. C sound. There we are. All right, so processing.sound, getting a sound file, calling music clip, getting audio in called microphone, using beat detector, amplitude, waveform. So here we want the active sound to be the music clip. So running it. Right, so we had that before. Let's get rid of the music clip. Right, so you saw how that was working. Back to the microphone. There's amplitude. All right, so I'm taking the input, but I'm not playing the input. Right, so it's analyzing what's going on the microphone, but not pumping it back out to the speaker. Right. So here you have various amplitudes. We have a beat recognizer. This is the beat recognizer here. The amplitude is here. I scaled it only on the y-axis, so it looks like a mouth. The louder I go, the bigger the mouth is, right? And then beat detector. Works some of the time. And we also have the frequency analysis. So the different components, different frequencies of the sound are shown in this bar. So when you go lower, it's lower down here. When you go higher, it's more over here, hopefully. So all these are, interesting little toys to play with, different bits of analyses. Let's see what it does when I do this. A little trinket from my trip. Let me know if you recognize this tune. Check. So it's a little bit of echo. And you get the mournful qualities. Oh gosh. There we go. And you get to experience the mournful qualities of a music box running out of energy. All right. What song was that? Do we recognize the tune? It was the opening theme to Final Fantasy. Yeah. A music box from the Square Store called Opening Theme from the original, from Final Fantasy 1. All right. Well, I wanted to have just a few minutes here at the end of class. We have 10 minutes. Are there any other topics you want to talk about? Like, this will be our last in-class time to do some like question answer discussion, to slate curiosity outside of like office hours, to chat a little bit more, in free-form manner. We haven't done a lot of that in this class. But do you have anything you want to talk about? Any processing things you're curious about? Any digital media or art applications that you'd like to get a take on? Yeah.
You touched on it earlier that like the three-dimensional aspect could be like a movie, or it is like a movie in terms of setting the scene and all that. Has
Yeah.
animation been done in processing the way it's been done in Blender before? Like actually making scene-by-scene movies or something like that, or short films?
Yeah. People have done interactive or filmic or moving and animated things in Blender. A lot of it's done procedurally, but that is a form of animation, a more algorithmic form where the crunch to bit ratio is different. So what I mean by that is if you make a movie in Blender and you import it, and you run that in processing, it's almost all, you're just displaying the data that's coming in, right? But if you, let's say, are in demo scene, you do a demo scene project in processing, there is the only data is the code. And so all of the shapes, we're specifying in code what all those vertices are. We're not taking them from an external object. We're making those ourselves. We're scaling them, rotating them, moving the camera, moving the lighting. All that's done with code. Even the color of things, even the texture of things is all done in code. So that makes, there's very little data coming in, which makes everything has to be calculated on the fly. The crunch is much higher compared to the data ratio. So this is important when you're talking about like generating things or interactive experiences. What are you taking in as assets? What are instantial things coming in that you simply just plop on the screen versus what are you creating with your algorithms dynamically? Yeah, so both movies have been done with both of those things in processing. And typically they're not like full-length movies, right? They're smaller experiences or things that simply randomly repeat for a long time, like an endless runner. You're welcome. What else? Yeah. Could you say that just a little louder? Sorry. Study outline for the final. We can have office hours. We can give you one of those. I have one of those half prepped. I don't have a schedule for it yet, but next week seems like a reasonable time.
I guess kind of a follow-up question. What day is the final to be, or I guess what day is the final going to be on?
Let's go to the syllabus and take a look. It's Tuesday of finals week at 3 to 5:30, but I'll show you exactly and how to find it on your own. Okay, browser. Let me just pull this up here. All right. Right, go to the syllabus. Finals meeting date, December 12th, 3:30 to 5:30.
And here, right?
Yes. It'll be the same format as the midterm. Same basic experience, just longer, covering comprehensively the material through the course. What else you got? Yeah.
You kind of showed this already, but I guess in a more dramatic sense. I think actually we saw an example earlier in the quarter. I might be wrong.
Mhm.
I never get sense, but what if like did input and then just a bunch of things would like show up depending on like the intensity of the audio. Is that something possible?
Yeah, you can do that. So basically, if you have the intensity, well, what is intensity of audio, right? Are you talking about sound? Are you talking about pitch changes? Are you talking about like multiple simultaneous frequency bands? Like, yeah, amplitude. So that example that we showed, going back to it. Microphone not playing. Amplitude. This is the amplitude analyzer. So it's taking a sound stream and it's trying to infer how loud it is. What's the volume, aggregate volume, which is a little difficult because you have a bunch of different frequencies coming in all at different volume levels. So it's actually looking across the spectrum of sound and boiling that down to one float number of amplitude or loudness. So you could use this float output. It gives you, a small number, usually between 0 and 1 value, and use that however you like. In this case, I'm scaling an ellipse, the y-axis of an ellipse, or the y-scale. Oh, I'm sorry. Go ahead. What? Help me understand.
I just meant like multiple elements popping up, like randomized of sorts, not just one element. Does that make sense? Not just manipulating element, but
You mean like when we did the stars thing, was like a bunch of different?
Yeah,
She means like a bunch of different random objects randomly populating, or like when we did the cars assignment, where it like randomly populated the screen full of objects.
but
Yeah.
manipulated through the audio.
Yeah, you could absolutely do that. So how would you do that? So there has to be some mapping of amplitude to some configuration of the random generation process, right? So perhaps amplitude, the higher the amplitude, like you cut down the time between generating the next thing, right? So things could appear more often. Or you could have a multiplier. When you hit certain amplitude thresholds, you generate more than one thing at a time. So you'd have to have like some design mapping of that sound value to your generation, right? Which is totally possible, right? Those were two quick examples. You could change like some generation algorithms simply have a chance of happening every frame. As the volume goes up, you increase that chance a little bit. So more things would happen on average per frame when things are louder. But there are a bunch of ways to do this mapping, and hopefully that gets you started. All right, last chance. Certainly you are all curious, multifaceted individuals that contain multitudes. Yeah.
Are the examples we went over today going to be like posted in the Google Drive?
They already are.
Okay.
They're there.
Perfect. 'Cause I'm definitely going to use this excluded.
Excellent, excellent. And I've uploaded all the videos, so I'll be posting those today too. All right, you'll also be getting course evaluations next week. Please fill those out. Those mean a lot. I'm happy to take feedback in person too. I put games out into the world those games have been on like YouTube videos. I've had all the gnarly comments in the world given to me, so pretty thick skin. But I like feedback so I can make this class better. This is the first time I taught this course from someone who had taught it for a long time before, so I'm taking like the course materials and putting my own spin on it. I'm sure I didn't do a perfect job. I'm happy to do better next time. I teach it again next year. So if you have any notes for improvement, happy to take them. I love crit. All right. Going once. Going twice. I think we're done. Thank you for your time. Hopefully you enjoyed today's lecture. Hopefully you enjoyed the lectures. I'm very much looking forward to enjoying your presentations next week. And we will put together some study office hours. I'll probably run something for the final for you to ask questions and give you a better idea what's going on. So stay tuned. Thank you, and have a great day and weekend.